no changes needed. When you tap a message into your phone, send a photo across the globe, or ask your smart assistant a question, you are relying on a bustling world of protocols beneath the surface, each with a distinct job to perform. Think of these protocols as teams of translators, security guards, and traffic controllers, all working together to make digital conversations not just possible, but seamless. These teams are organized by specialty. Some manage the raw delivery of data, others coordinate how that data is packaged and sent, and a select few give meaning to the information so that applications like email clients or web browsers can understand and use it. To unravel how all this happens, it helps to distinguish between the core types of communication protocols and the crucial roles each one plays. At the most fundamental level, networking protocols are grouped according to their primary purpose: facilitating communication, managing network operations, or ensuring security. Communication protocols are the stars of the show, enabling devices, no matter how different in design or purpose, to interact and exchange information. These include protocols for both analog and digital communication, from those orchestrating the flow of data across the internet to those embedded in the tiniest sensors of an industrial machine. Management protocols, meanwhile, quietly oversee the health and functioning of complex networks, while security protocols shield sensitive information and guard against prying eyes. The frameworks used to organize and understand these protocols are the Open Systems Interconnection Model and the Transmission Control Protocol/Internet Protocol Model. The Open Systems Interconnection Model serves as a theoretical map, while the Transmission Control Protocol/Internet Protocol Model powers the real-world Internet. Both models break networking tasks into layers, each with its own collection of protocols and specific set of functions. For our purposes, 3 layers matter most: the network layer, the transport layer, and the application layer. The network layer is where the journey of each packet of information truly begins. Here, the focus is on routing and forwarding data from one node to another, across potentially vast and intricate networks. Protocols in this category handle the logistics, charting the best path, ensuring each packet reaches its destination, and adapting to changing conditions along the way. The Internet Protocol, or IP, is the backbone of this layer, assigning addresses to devices and guiding data through a maze of interconnected networks. Supporting IP are protocols like Internet Control Message Protocol, which assists in error reporting and diagnostics, Address Resolution Protocol, which maps network addresses to physical hardware addresses, and routing protocols such as Routing Information Protocol and Open Shortest Path First, which help routers communicate and determine the most efficient routes for data. Moving up a layer, we reach the transport layer, a crucial intermediary responsible for moving data from one application to another safely and efficiently. The 2 best-known protocols here are Transmission Control Protocol and User Datagram Protocol. Transmission Control Protocol, or TCP, is the meticulous worker of the pair. It breaks large messages into smaller packets, numbers them for tracking, and ensures each packet arrives intact and in order. If a packet goes missing, Transmission Control Protocol notices and requests a retransmission. This reliability is essential for applications where every piece of information matters, such as file transfers or web browsing. In contrast, User Datagram Protocol, or UDP, values speed over perfection. It sends packets without worrying about order or delivery confirmation, making it ideal for real-time applications like voice calls or online gaming, where a lost packet is preferable to a delayed one. The transport layer also manages multiplexing, allowing multiple applications on a device to share the same network connection without interfering with each other. Above the transport layer lies the application layer, the domain of user-facing protocols. These protocols do not move data themselves, but instead define how software applications communicate over the network. Each is tailored to a specific type of task, whether it is retrieving web pages, transferring files, sending emails, or resolving domain names. HTTP, the Hypertext Transfer Protocol, is perhaps the most recognizable, forming the basis of communication between web browsers and servers. Whenever you load a website, HTTP governs the requests and responses, dictating how text, images, and videos are fetched and displayed. FTP, or File Transfer Protocol, specializes in moving files between computers, providing a set of commands for uploading, downloading, and managing files on remote systems. SMTP, the Simple Mail Transfer Protocol, handles the sending of emails from one server to another, while POP and IMAP offer ways to retrieve and manage those emails on your device. Other application layer protocols fill equally vital roles. DNS, the Domain Name System Protocol, translates human-friendly website names into the numerical addresses computers use to find each other, a kind of digital phone book for the internet. DHCP, or Dynamic Host Configuration Protocol, assigns IP addresses automatically to devices joining a network, ensuring that each one can communicate without manual setup. Telnet and SSH provide remote command line access to servers, with SSH adding robust security to the connection. SNMP, or Simple Network Management Protocol, allows administrators to monitor and manage network equipment, collecting statistics and sending alerts when problems arise. Protocols are not limited to sprawling global networks, they are just as critical in specialized environments. In instrumentation and automation, protocols like RS-232 and RS-485 govern communication between sensors, controllers, and computers. Embedded systems, found in everything from cars to medical devices, use their own protocols such as UART, SPI, I2C, CAN, and Ethernet, each chosen for its balance of speed, reliability, and complexity. The interplay between these protocol types is what makes modern digital communications so resilient and adaptable. For example, when you upload a photo to a website, the application layer protocol, HTTP, defines the rules for your request. The transport layer protocol, usually TCP, ensures each piece of the image arrives in the correct order, and the network layer protocol, IP, routes those pieces across the internet. At every step, management and security protocols may be quietly at work, SNMP, monitoring the health of the network, SSL or TLS, encrypting your data, and firewalls applying rules to keep out unwanted traffic. Communication protocols can also be described by how and where they operate. Some are inter-system protocols, managing data exchange between distinct devices, while others function within a single system, coordinating processes internally. In distributed systems like those powering cloud services or financial networks, protocols must coordinate the actions of many independent computers, sometimes using synchronous communication for real-time tasks such as HTTP or Remote Procedure Calls, RPC. All these protocols work together to solve the challenges of digital communication, moving data quickly and reliably, resolving addresses, securing transmissions, and managing the complex networks that connect our world. Whether you are streaming a movie, checking your bank balance, or controlling a factory robot, the invisible choreography of network, transport, and application protocols ensures that every message finds its way in the right order and in the blink of an eye. Imagine a conversation between two computers separated by continents, each tasked with sending and receiving a flurry of messages, sometimes within fractions of a second. How do these machines, communicating in the silent language of ones and zeros, ensure that every instruction and every piece of data is understood exactly as intended? At the heart of this intricate process are communication protocols, systems of rules so precise and layered that, to the untrained eye, their complexity resembles a symphony orchestra, where every instrument must play its part flawlessly for the music to make sense. To understand how protocols manage this feat, picture the process as a series of steps, each governed by its own set of responsibilities and mechanisms. This methodical approach is captured in what is known as the OSI model, a conceptual framework that breaks down the journey of a message into 7 distinct layers. Published in 1984 and still foundational for understanding protocol interactions, the OSI model assigns each layer a specific role, from the raw transmission of electrical signals to the nuanced exchanges between software applications. At the lowest level is the physical layer, responsible for the actual movement of bits across wires, fiber optics, or even through the air. Here, the protocol is unconcerned with the meaning of the bits. It only ensures they travel from one device to another, uncorrupted and at the right time. Above this, the data link layer takes those raw bits and bundles them into frames, adding mechanisms to detect and correct errors that might occur during transmission. This error detection often involves adding specialized codes or checksums to the data, so that if a frame arrives with a problem, the receiving device can either fix it or request a new copy. Moving up, the network layer ensures that information does not just travel between 2 points but can traverse entire networks, passing through routers and switches that guide it along the most efficient path. The transport layer, meanwhile, is the master of reliability and flow. It divides large messages into manageable segments, numbers them for reassembly, and orchestrates their journey so that nothing is lost or delivered out of order. This is where flow control comes into play, a system for managing how much information can be sent at once, ensuring that neither side is overwhelmed and that the connection remains smooth. One of the most critical mechanisms at this stage is the handshake. While the term may evoke images of a business meeting, in the world of protocols, handshaking is a carefully choreographed exchange that sets the rules for communication before any actual data is transferred. The handshake procedure allows devices to synchronize, confirm each other's readiness, and agree on parameters like message size and error handling methods. In modern digital networks, this is most famously exemplified by the three-way handshake used by the Transmission Control Protocol, or TCP. When two computers want to establish a reliable link using TCP, the process begins with the initiating computer sending a special packet, a segment with a synchronization request. The receiving computer responds with its own acknowledgement and synchronization, and finally, the initiator sends a confirmation. This three-step ritual ensures that both sides are aware of each other, prepared to manage the data flow, and can identify any problems from the outset. Every segment sent during a TCP session carries a header packed with valuable information: port numbers to identify applications, sequence numbers to keep packets in order, flags to signal specific actions, window sizes to control flow, and checksums for error detection. If a segment is lost or corrupted, TCP's error control mechanisms activate, triggering retransmissions and keeping the conversation on track. The art of error detection and handling does not stop at the transport layer. Each segment of a protocol stack from the physical layer up has its own approach to identifying and correcting mistakes. Some protocols use predefined structures, codes, or specialized messages to report errors, requiring both ends of the connection to monitor for issues and respond appropriately. The process might involve automatically resending data, adjusting transmission rates, or even renegotiating the connection if persistent problems arise. This vigilance is essential for ensuring that instructions and information are not just sent, but received as intended, without distortion or loss. While error handling is critical for reliability, protocols must also manage the pace of communication, a challenge known as flow control. Imagine one device that processes data quickly and another that lags behind. Without flow control, the faster device might overwhelm its partner, causing data to be lost or ignored. Protocols address this by allowing the receiving side to advertise how much data it can handle at any given moment, and the sender adjusts its rate accordingly. In Transmission Control Protocol, for example, this is managed using a window size indicator within the segment header. If the window shrinks, the sender slows down. If it grows, transmission speeds up. This dynamic negotiation ensures a balance between efficiency and reliability. The layered design of protocol models like open systems interconnection offers several advantages beyond mere organization. By segmenting responsibilities, each layer can evolve independently, allowing developers to innovate or troubleshoot without disrupting the entire system. If a new method for error detection is devised, it can be implemented at the data link or transport layer, while higher-level applications remain unchanged. This modularity is a cornerstone of modern network design and a key reason why the open systems interconnection model, even as real-world networks often use the streamlined Transmission Control Protocol/Internet Protocol model, remains a reference point for understanding how protocols interlock and operate. Transmission protocols, regardless of their specific type, all share the same fundamental goals: to package data into well-defined units, transmit them reliably, acknowledge receipt, and reassemble the original message at the destination. The process may seem automatic, but it depends on a delicate interplay of handshakes, error checks, and flow adjustments. In embedded systems, these rules extend to the definition of signal formats, precise timing, and synchronization mechanisms. By standardizing how devices communicate at every step, protocols reduce the complexity of integration and boost consistency, a vital benefit in environments where reliability is non-negotiable. As technology continues to advance, the mechanisms that underpin protocols become ever more sophisticated, but the core principles remain the same. Define a clear structure for messages, build in systems for detecting and correcting errors, and ensure that the conversation flows at a pace both sides can handle. Whether it is a sprawling data center or a simple sensor network, the invisible machinery of protocols works tirelessly behind the scenes, transforming raw data into meaningful, reliable communication. In the chapters ahead, we will explore how these mechanisms adapt to new challenges, from securing data against threats to supporting the demands of global-scale cloud systems. For now, it is enough to appreciate the rigor and ingenuity that make digital conversations possible, one layer and one handshake at a time. Imagine the simple act of sending an email to a friend, asking how their day went. Beneath that everyday experience lies a choreography of communication protocols, each playing its part to ensure your words arrive intact, remain private, and can be trusted. The invisible machinery of these protocols makes digital communication not just possible, but safe and reliable. Let us explore the real world of protocols in practice, tracing their paths through the technologies we use every day and discovering how they shield our information from prying eyes. When you press send on your email, a sequence of protocols springs into action. The Simple Mail Transfer Protocol, or SMTP, is responsible for delivering your message from your outbox to your recipient's mail server. But the process does not stop there. Your friend's device, whether a laptop or a smartphone, uses other protocols like IMAP or POP3 to fetch and organize the message, ensuring it appears neatly in their inbox. Each of these, SMTP, IMAP, and POP3, has a specialized role, working together to move messages across the digital landscape. The web itself extends these email practices even further. Many people now access their messages through webmail services like Gmail or Outlook.com, which use HTTP, the same protocol that loads your favorite websites to let you read, compose, and manage your correspondence in a browser. Behind the scenes, these services still rely on the core email protocols to move your messages between servers, but the interface you see is made possible by HTTP's ability to flexibly deliver content to your screen. Yet, as seamless as these interactions may seem, the journey of an email is full of risks. Cybercriminals are constantly devising new ways to intercept, fake, or manipulate messages. Imagine a world where anyone could send an email pretending to be your bank, or where your private correspondence could be read by strangers along the way. To prevent such threats, email protocols have evolved to include robust security measures. Authentication is a vital first step. It ensures the sender of an email is truly who they claim to be. Protocols like SPF, DKIM, and DMARC work together to verify the legitimacy of sending domains, making it much harder for malicious actors to forge messages or impersonate trusted contacts. Encryption is another essential defense. Without it, the contents of your messages would travel the internet in plain view, vulnerable to interception by anyone with the right tools. Security protocols such as SSL and TLS, and their email-specific versions like SMTPS, wrap your communications in layers of complex mathematical protection so only the intended recipient can decipher them. This is especially important when sensitive data like passwords, financial information, or confidential business plans passes through email. But the story does not end with email. Messaging protocols power a vast range of digital conversations, both asynchronous, like email, and synchronous, like instant messaging or chat rooms. In synchronous settings, protocols used in chat apps or IRC, channels must not only move messages quickly and efficiently, but also ensure that conversations remain private and authentic. These protocols are designed with user experience in mind, balancing speed and security so you can chat with friends, coordinate with colleagues, or participate in global discussions with confidence that your words are protected from tampering or eavesdropping. Security, however, is not just a technical matter. Human factors play a critical role as well. Even the most sophisticated protocol can be undermined by weak passwords, careless sharing of sensitive information, or falling for phishing attacks. That is why best practices for email and messaging security emphasize not only encryption and authentication, but also user awareness and education. Access controls limit who can read or modify messages, and organizations increasingly invest in training users to spot suspicious activity and handle information responsibly. The web, too, is a battleground for privacy and security. When you log into a website, post a comment, or make a purchase, HTTPS, the secure version of HTTP, encrypts your data as it travels between your device and the server. This helps protect your personal information from being intercepted or altered. But securing web applications involves more than just encryption. Input validation is crucial to prevent attackers from injecting malicious code or exploiting vulnerabilities. Strong passwords and two-factor authentication add further layers, making it much more difficult for unauthorized users to gain access. Data security and privacy are not just technical ideals, they are legal obligations. Regulations such as the General Data Protection Regulation and the California Consumer Privacy Act set rigorous standards for how organizations must handle and protect personal information. These legal frameworks require companies to implement protocols that safeguard data confidentiality, control access, and ensure information is available only to those with a legitimate need. Encryption, access controls, and careful data classification all play their part, with privacy notices serving as a transparent promise to users about how their information will be used and protected. Yet, despite all these defenses, privacy incidents still occur often because of improper controls when accessing or sharing sensitive data. A single misconfiguration, a lapse in user vigilance, or an outdated protocol can open the door to data breaches, financial loss, and reputational harm. Real-life examples abound of organizations suffering from the consequences of exposed systems, underscoring the importance of continuous security education and proper configuration. To help organizations understand and address the most critical risks, the security community maintains resources like the OWASP Top 10, a regularly updated list of the most significant web application security threats. By following these guidelines, developers and administrators can test for vulnerabilities like SQL injection or cross-site scripting, prioritize remediation efforts, and ensure their defenses are working as intended. Security, in this modern landscape, is not a one-time checklist, but a continuous process of detection, prioritization, and improvement. Beyond personal devices and corporate servers, communication protocols are now woven into the fabric of our physical world. The rise of the Internet of Things networks of connected devices from thermostats to industrial sensors relies on specialized protocols like REST over HTTP, COA, PMQTT, WebSocket, and AMQP. These protocols are chosen for their ability to transmit data efficiently, even in environments with limited power or bandwidth. Whether connections are wired or wireless, the right protocol can mean the difference between a secure, scalable Internet of Things network and a vulnerable, inefficient one. Ultimately, the protocols at the heart of our digital lives do far more than shuffle data from place to place. They are active guardians, enforcing rules, verifying identities, encrypting secrets, and adapting to new threats as technology evolves. Their success depends not only on technical brilliance, but also on the vigilance of users and the strength of organizational policies. Every time you check your email, send a message, or browse the web, you are witnessing the silent labor of these protocols, working tirelessly to keep your information flowing smoothly, safely, and securely. As our world becomes increasingly connected, the invisible architecture of communication protocols is undergoing a profound transformation. Today, the scale and diversity of digital devices surpass anything seen before. In particular, the rise of the Internet of Things, or IoT, is reshaping how machines, sensors, and even everyday objects interact. The numbers are staggering. Projections estimate there will be over 41 billion IoT connections by 2030. This explosion in connectivity is not just about quantity, but also about the complexity and variability of the conversations taking place between devices. Each device, whether it is a smart thermostat, a wearable health tracker, or an industrial sensor, comes with its own set of requirements and constraints. Some need to transmit tiny bursts of data with minimal power consumption, while others must handle continuous streams of critical information. To meet these demands, a new generation of protocols has emerged, each designed to address specific use cases and technical challenges. Protocols like AMQP, Bluetooth, and LoRaWAN illustrate the range of approaches in use today. AMQP, for example, is well suited for reliable, secure messaging between enterprise systems and cloud services. Bluetooth, with its low power requirements, is ideal for personal devices and short-range communication. LoRaWAN, on the other hand, excels at enabling sensors to send small packets of data over long distances while consuming minimal energy. These protocols are carefully selected to balance speed, power consumption, security, and interoperability, a delicate mix that becomes increasingly important as IoT deployments scale. A central challenge as the number of devices multiplies is ensuring that they can all communicate effectively. This is where the foundational OSI model continues to play a key role, providing a framework for interoperability and ongoing maintenance. Standards organizations, such as the IEC and the IEEE, are actively evolving the rules and frameworks that govern how IoT devices communicate. Their work is vital in ensuring that new protocols do not become isolated islands, but instead remain part of an integrated, future-proof network. The stakes are high. Without common standards, the promise of a seamlessly connected world would quickly unravel into a patchwork of incompatible systems. The unique requirements of IoT have also driven the development of specialized application layer protocols. Unlike traditional internet protocols, which often prioritize throughput and general-purpose connectivity, IoT protocols such as MQTT, COAP, and WebSocket are tailored for environments where bandwidth and energy efficiency are paramount. For example, MQTT is designed for lightweight messaging, making it ideal for scenarios where devices have limited computing resources and intermittent connectivity. COAP, meanwhile, provides web-like interaction for constrained devices, using a minimal overhead approach that conserves battery life and network capacity. Choosing the right wireless protocol for IoT is more than a matter of convenience. It directly impacts device performance and longevity. Some protocols are optimized for ultra-low power operation, allowing battery-powered sensors to function for years without maintenance. Others focus on minimizing latency or maximizing range, depending on the needs of the application. As deployments expand to thousands or even millions of devices, these choices become critical for both technical and economic reasons. Running parallel to the evolution in IoT is the arrival of 5G, a technological leap that is revolutionizing the foundations of communication networks. 5G is not just an incremental improvement in speed. It offers a fundamentally new architecture with capabilities that support real-time decision-making, cloud integration, and secure mobile operations across both government and industry. Its ultra-reliable, low-latency communication makes it an enabler for critical infrastructure and the industrial Internet of Things, where milliseconds can make the difference between safe operation and catastrophic failure. The architecture of 5G introduces new protocols and security measures, with international bodies like 3GPP, ETSI, and the IETF working to enhance network security and resilience. Protocols such as EAP, TLS, and OAuth2 are now woven into the fabric of 5G networks, providing advanced authentication, encryption, and privacy protections. These measures are designed to address the growing challenges of securing vast, highly distributed networks and to protect against evolving threats targeting both individual devices and entire network segments. Beyond security, 5G's promise lies in its ability to support a new wave of applications: augmented reality, remote surgery, autonomous vehicles, and more, by delivering data at unprecedented speed and reliability. Businesses are already leveraging 5G's capabilities to enable real-time collaboration and advanced Internet of Things solutions, transforming how organizations operate and interact with customers and partners. Looking even further ahead, the drive for connectivity is extending beyond terrestrial networks. Satellite communication systems are being integrated with both 5G and the anticipated 6G technologies, forming a truly global web of connectivity. This integration is expected to bring high-speed, reliable access to remote and underserved regions, further breaking down barriers to information and economic opportunity. Another trend shaping the future of communication protocols is the integration of artificial intelligence and the early promise of quantum computing. Artificial intelligence is already being used to manage and optimize network performance, with intent-based autonomous networks emerging as a hallmark of next-generation infrastructure. These networks can self-configure, adapt to changing conditions, and even anticipate problems before they arise, all guided by artificial intelligence-driven decision-making. The evolution of agentic artificial intelligence also points to a future where decentralized internet protocols allow autonomous agents, software programs acting on behalf of users or organizations, to interact and negotiate directly without human intervention. Quantum computing, though still in its formative stages, presents new challenges and opportunities for protocol design. Traditional methods of protocol testing and validation may no longer suffice, requiring more intelligent, integrated approaches that can accommodate the unique characteristics of quantum data and operations. The network topologies of the future, shaped by the Internet of Things, cloud computing, artificial intelligence, and immersive technologies like augmented and virtual reality, will demand protocols that are both flexible and robust, capable of scaling seamlessly while maintaining the highest standards of security. As data volumes continue to soar and the number of connected devices multiplies, the work of evolving and refining communication protocols has never been more important. The standards that govern 5G, 6G, and Wi-Fi are setting new benchmarks for bandwidth, latency, and energy efficiency, defining the contours of tomorrow's wireless landscape. At the same time, organizations responsible for maintaining these standards are focused on ensuring interoperability, security, and long-term viability, recognizing that the choices made today will shape the possibilities of the future. Ultimately, the future of communication protocols is not just a story of technical evolution, but of global collaboration and shared vision. The challenges are immense, but so are the opportunities. As protocols adapt to new technologies and ever more ambitious applications, they will remain the silent but essential conductors of our interconnected world, a world where every device, every signal, and every bit of data is part of a vast, harmonious conversation.